And welcome to my new video. This time I'll be talking about polar distributions for a second time. In the first video about polar distributions, we used the planar polar distribution to build up an erythrocyte. This time we will be using a 3D polar distribution and we will obtain a random, irregular roundish structure, necessary for modeling things like leukocytes or enveloped viruses. While 3D seems to be more complicated than the 2D planar distribution, it will be actually much more easy. We want an irregular structure, so we leave most of the work to random numbers. All portrait scripts to this video and to all other videos from this playlist can be found in my GitHub account. You can find the link to this GitHub account in the comment section to this video. For a start, let's recall the differences between Cartesian and polar distributions. Cartesian distributions use the three coordinates x, y, and z to specify a given position in space. In the case of polar distributions, we use one coordinate, here the x coordinate, and two angles, here around the y and the z axis, to do this. How can we generate a random 3D polar distribution in Porphyry? Here's the short outline. For a start, we have to define the number of elements we want to distribute and the maximum radius of our distribution. Then we define a loop where we define the position for each of our elements one after the other. For this, we first define a random position on the x-axis between 0 and the maximum radius. Then this random position is rotated around the y and the z-axis. Both times, a random angle between 0 and 360 degrees is used. Finally, a sphere is placed on the position just defined. Using this approach, we end up with a structure like this, a random spherical cloud of little spheres. By enlarging these spheres and fusing them into a blob, we reach the irregular roundish structure we were looking for. The larger we set the radius of individual spheres, the smoother the surface of this blob will become. And why should we need such structures? We can use such blobs as the basis for enveloped viruses, like this AIDS virus, for example. Spherical distributions are not restricted to distributing spheres. Other things may be distributed as well. Here it's the cells of the cyanobacterium aphanotica, which are comprised inside a roundish ball of slime. These were two examples how we can use spherical 3D polar distributions for modeling natural structures. In my next video, I will show you a number of applications of 3D Cartesian distributions.